Guys, welcome to our channel of Sciences and Mathematics. Today's topic of discussion is basically going to entail the summary of what we have already discussed, and that is the concept of a scalar product. Now, I felt that this is important because there are some of the areas that we have dealt with independently, and there are some, of course, which may need to be pulled up together so that we can be able to apply them in a specific or an appropriate way in case we come across them. So for that case, thank you and welcome. So as I've mentioned, today's topic is going to be basically a summary of the concepts of all the concepts that we have discussed in the dot or scalar products. And this is going to assist us in case maybe we need to apply a concept in conjunction with another one. And that is going to assist us, of course, in solving some of the problems that we may come across. So basically we say that a scalar or dot product of two vectors A and B. Let's assume that we have two vectors A and B. The scalar product of those vectors is going to be defined as A dot B is equals the cosine of theta, where now that we have said A and B are vectors, so therefore where this one implies the magnitude or modulus of A and B implies the modulus of vector B, and theta is the angle between just between A and B. So theta is the angle between vector A and B. So therefore, given this particular definition, we can see that there is an element of angle that is involved in this particular definition, and therefore we have the concept of modulus and the dot product. So in our previous video that we have discussed about the concept of a dot product, we're going to see that some of those characteristics are going to apply here, and then the concept of a modulus or a magnitude and the cosine of this. So even maybe two of these characteristics, we can be able to make one a subject of the other and try to make a definition from that. Now, as we said that a dot or scalar product is a measure of how closely two vectors align in terms of their direction or in the direction in which they point. I can maybe be able to illustrate the two vectors for A and B just using that arbitrary example from a point of origin, maybe that one. So this basically defines, the cosine of theta defines the angle between the two vectors for A and B respectively. Now, last time when we were trying to talk about vectors, we put the concept of Pythagoras theorem, and that one was applying to right triangles, and they assisted us to find the different sides of a right triangle, given maybe one side of that and the angle that appeared in between. We gave an acronym for definition of different trigonometric functions for the angles for the sine of theta, the cosine of theta, and the tan of theta, as the sine of theta is given as opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and the tan of theta is the opposite over the adjacent in that specific order. Now, suppose we have maybe a specific illustration that I'm going to give of this is a vector x, this is a y, and this is x, and then there's a vector that is going out that way at an angle theta. And we try to make a right triangle from that specific point, and this is vector A, B. Therefore, from this one, we can be able to do a representation of maybe using Pythagoras theorem. Now that this is specific and at this point is 90 degrees. So therefore, we can be able to just illustrate at the cosine of theta equals adjacent over the hypotenuse, therefore which we have written as A all over B. So that's how we can be able to define the cosine of theta. Now suppose I want to find the quantity, or maybe a description for the quantity of A, or for A. Therefore, given that the cosine of theta is equals A over B, implying I can describe A as B the cosine of theta. So in this case, therefore, I'm going to do a substitution for this A, and then write B the cosine of theta at that specific point. So therefore, we can be able to illustrate those vectors as vector B and B the cosine of theta. So that is going to give a relationship between what we're going to discuss. Now suppose this one was A, vector A, then still I'm going to represent that one using A, no, not that one, sorry for that. So this is for B, cosine of theta. So let's just retain this one like this so that we can not create an ambiguity. So in this case, I'm going to represent this one using a B, the cosine of theta, for that specific value for A that I've written on that board. So we're going to see that there's a specific characteristic for this dot product, that we say that suppose A is equals B, then we can be able to write this one as B, A, and this is a characteristic of the dot product that we say that they are commutative. So therefore, this is one of the characteristics that is going to assist us to just do a summary, or maybe try to look at some of the characteristics of dot products or scalar product. And we talked about the concept of a unity vector in one of our videos. So I'm going on so to illustrate it here and try to see how it has a relationship with other concepts that we have discussed about. So therefore, we say that for a vector in a rectangular coordinate system that is having the x, y, and z, which is represented as I, j, and k, it's a unity vector. A unity vector implies that the x component is 1. So for a unity vector, x component is 1, which is represented by I, and then the y component, y component, which is represented by j, z component is represented by. Okay, so therefore, that's a three-dimensional representation of that specific vector. And we found out that if we try to do a cross for I dot I, then this is going to give us 1. Now we can be able to illustrate this using the specific formula that we have given for dot product, which is A dot B is equals the modulus of A, or the magnitude of A, magnitude of B, the cosine of theta. Now given that our A plus B here is representing vectors that are moving in the same direction, or just a similar vector, which is I dot I, this is going to give us the modulus of I, the modulus of I, the cosine of theta. So a vector that is moving in a which does not have a, maybe just give an illustration for that. Maybe this is the x, which is the I direction. This specific vector does not maybe create an angle that is going to be between them. So therefore, this is going to be the cosine of 0. I mean, theta is going to be 0 degrees. So therefore, from that point, we're going to see that the cosine of 0 is equals 1. So this being a unity vector, so therefore the concept of unity implies that the I and j, I mean the I direction is just 1. So basically the modulus for 1 is 1, and then for 1 is 1. The cosine of 0 is 1. So therefore this is going to give us a product of 1, which basically implies to our rule that we have already stated here. So so basically using that analogy for the I, j, and k, so this the dot product of these specific components similarly are going to give us 1. So that's one of the characteristics that we talked about. But for the dot product of these different components, that is either I, k, or j, k, or I, j, this is going to give us 0. And of course, we have talked about the concept of an orthogonal, which is 90 degrees. So basically, we're going to see that this specific, the dot product of these specific vectors that we're going to multiply, like the ij, this is 90 degrees, jk, this is 90 degrees, and then ij, or ik, this is also 90 degrees. So therefore, when we're doing a dot product of two vectors which are 90 degrees, or maybe orthogonal to one another, then it's going to give us 0. So again, there's one of the properties that we discussed about the dot product of vectors, and this is the concept of the products being distributive, in a way that if we try to multiply the vectors by, or the cross the vectors by a specific vector, we are going to get that it's going to give us, let's give an example. That is a plus b, a dot a plus b. Sorry for that. This is going to give us ab plus ac. So this property of vectors is known as distributive. In that when we multiply a times the components of those, or maybe these vectors which are in brackets, it's going to give us that specific product. So in this case, of course, we're going to look at the combination of the unit vectors that we have talked about, and some of the behavior we're going to see if we maybe to do the cross product of a vector like AB. Now remember, in a three-dimensional space, we give the components of vector A as AXI plus AYI plus AZK. This is J. So these are the components of vector A. You can just use that one around the hearts. So for B also, we can be able to describe its components as xi plus by j plus b z k. So those are the two respective components of those specific vectors. Now the dot product of AB therefore is going to be represented by having the component of A and then we do a cross with the components of B. I'm going to, okay, just there's something I want to illustrate. I'm just going to put something over there. So we have a component of this one, and then B, Z, K. So we are having a dot product of those specific components. Therefore, this is going to be the sum of the A components plus the sum of the B components for those respective vectors. Now that we have talked about the concept of a unity vector, whereby the I is equals j equals k, which is going to give us 1. Those specific components are going to give us the product of 1. So therefore, for the first one, we're going to multiply the first component with the first from the second one for a. So the product for this is going to be x. Now that the I component has disappeared, plus ay by plus az bz. So that is going to give us the dot product of those two specific vectors. And we're going to see that this particular behavior is going to assist us, of course, in trying to find solutions to some of the vectors that we have discussed about. We can just do that one using one of the examples for the sake of just for our reminder, and then we can discuss, of course, about maybe just 1 or 2 examples for just illustration, and then we'll just do away with it. So I'm just going to do away with this. So suppose we are asked to find the scalar product. Find the scalar product of this specific vector given a equals 8i plus 2j minus 3k, and b is given as 3i minus 6j plus 4k. So we are asked to find the scalar product of those two vectors. So therefore the solution will be a dot b will be equal to 8i plus 2j minus 3k dot 3i minus 6j plus 4k. So we just do a multiplication of the respective components, and is 8 times 3 by 8. It's going to give us the I component plus, so using the last formula that we discussed, so plus this is 2 times this one, so this is negative 12, and then this is the last one is minus 12. So all of this is going to be 24 minus 12 minus 12, which is going to give us 0. So basically, this implies that this implies that the distance, I mean the angle between the two vectors that we have seen, as we have discussed about the concept of them being orthogonal, the angle between the two vectors for A and B is going to be a cosine theta, which is going to be imply theta is equals 90 degrees. So from the illustration that we had given for the cross for identity, or I mean the unity vectors, we said that the KKJJ is equals 90 degrees. And then we say that for this formula that we had been given for the dot product, this is, I mean the cosine of 90 degrees is equals 1. So therefore implying that if these two vectors are going to give us this specific characteristic, so therefore the angle between the two vectors is going to be 90 degrees. So this is just a behavior that we have just tried to connect with the other points that we have discussed, given that the product for this is 0. So therefore, we can also be able to find the angle between them by just making a division of this section of the formula at those specific points. And of course, we have already seen on how we can be able to find the modulus or the magnitude of vectors by finding the root of the sum of those, the root of the sum of the square of those specific components for x, y, and z. And that I presume that is going to be easier for us. So in that case, maybe we can just do an illustration for that, so that we do not assume that we are discussing the summary for this. Maybe we can just do an illustration for that one for the last, or maybe it will give us a clue. So if we are asked to find the angle between, find the angle between vector A, which is 2i plus j plus 2k, and B, which is given as 4i minus 3j. So for this, it does not have the k component, so this is the solution is going to be, we know that the formula A dot B is equals the modulus of A, the modulus of B, the cosine of theta. So therefore, we can be able to do that. So therefore, we can make the cosine of theta the subject of this specific formula, and therefore have the modulus of A, the modulus of B, represented as that. And doing a substitution for this, we are going to have the cross for those two specific vectors for A and B, and we say we just multiply the specific components. So therefore, the cosine of theta is going to be 2i plus j plus 2k into, this is 4i minus 3j. So basically for that one, the k component is going to disappear, as I said. So this one is over. The modulus of that first vector, of course, just going to take a root, a short graph for the sake of space. It's going to be the square of this component, the sum of the square of those components, implying 2 squared, which is 4, plus 1 squared, which is 1, plus 2 squared, which is 4. And then we're going to do a cross, or just a multiplication with this second one, which is 16, the root of I squared, that's 4. So this is going to be 16 plus this is going to be 9. So therefore, we are going to have this one represented as, this is going to give us 8 minus 3 plus 0 divided by, this is going to be 16. So therefore, the square root for that is going to be, no, that's not going to be 16, it's going to be 9. So the square root for that is going to be 3 times, this is the root of 25 is 5. So therefore, this is going to give us a third. So implying the cosine of theta is equals a third. So for us to find the angle between this one, we are going to find the cosine inverse, the cos inverse of theta, which is going to be 70.5 degrees. So the angle between these two vectors that we're trying to find out, information for that. In case you find the values not coming to this, kindly you can be able to mention it on the comment section so that you can be able to do rectification. So basically for that, the summary of the cross product and the characteristics that we talked about in some of our videos, this is going to assist us, of course, in trying to create a relationship between one concept and another. So that is it for today, guys. Bye. God bless.